But if we again look at the synergy equation, so this is the same equation as before, what do the values actually mean? Well, if we draw a plot, then if we have zero interaction between the two devices, then, well, that means there is nothing going on between them. If we get a positive interaction, that means that there is some sort of added value from combining the devices, so it's more than just the sum of their individual works. But if we get a negative synergy, then that means that there is some redundant flexibility. So both could do what the other does, but you cannot do that twice. So there is some redundancy there. So that's what the values of synergy will mean there. Okay, so that's all the principles, the approach. Now let's dive into the specifics of the evaluation that we did in the same paper. I'll just show a couple of highlights. There's a lot more that we did in the paper, but due to time, we cannot cover all of it, of course. So just bear with me, and we'll see the most interesting results. Important to mention here, this is for a winter scenario in the Netherlands. So it's cold, that means the heat pump has a lot to do. The sun is not shining as much, so there's not a lot of solar energy to shift. Okay, without further ado, let's look at the Shapley values of our specific devices. So here we are, these are them. What we see is that the electric vehicle, the battery energy storage system, and the heat pump have a comparatively high Shapley value, and perhaps unsurprisingly, the dishwasher and a heat pump, the dishwasher and a washing machine have a very low Shapley value. It's the washing machine, if I recall correctly, is roughly 100 times as low their Shapley value as an electric vehicle. So this really goes to show how much more important it is to control an electric vehicle compared to such a device. Okay, so that's it for the Shapley values quickly in this evaluation. Now I want to look at the synergy between devices a little more. So on the x-axis here, to understand the plot first, and then we'll dive into the results. But on the x-axis, we have the 5 devices that we talked about earlier, on the y-axis as well. So that means that every value is the synergy between those two devices. So a device with itself, zero synergy. So that's why we have zeros on the diagonal. And we also see that the plot is symmetrical across the diagonal because the synergy between an EV and a heat pump is the same as the synergy between a heat pump and an EV. Okay, that's how we interpret the plot. Now let's look at the result. What we see is, and what really stands out, is that the synergy between a battery and an EV is very, very negative right here. And it's by far the largest synergy value that we see. Perhaps that is a little bit surprising, but let's look into it some more, because this is in the situation that we have a maximum charging power of EV of 11 kilowatts. Now, if we change the maximum charging power of EV and we make it lower, so 3.7 kilowatts, one phase, then suddenly it turns around entirely. Again, it's the synergy between the EV and the battery that really stands out, but suddenly it's a very positive value instead of a very negative one. So that begs the question, why? Why is that? Well, let's dive into it some more again. So we still have the plots right here, but how did we really define the synergy between these two devices? Well, the interaction work is the worth of our coalition T and adding both the EV and the battery to it, minus these two terms where you just have the EV or battery, and then plus where you have neither. Now, if we control the EV, then what we discovered is that both of these cases, so the coalition where we control the EV and the battery, and the coalition where we just control the EV, those values remain constant regardless of the maximum charging power of the EV. To understand why, we have to look again at what it means to control a device. And what you see here is, remember at the top, we are not controlling any device. On the bottom, we're controlling all of them. So if we do not control the EV, we see that it just creates a very high peak. And the height of that depends on the charging power of the EV. But if we control it, we see that the charging power is, well, the highest is 2 kilowatts right here. So if the charging power of the EV is higher than whatever it needs here anyway, so regardless of whether it's 11 or 3.7, it will just be able to follow this here schedule. So if we control the EV, we get a schedule that is independent of its maximum charging power because it's going to be below that charging power all the time anyways. So that's why those two terms are constant. But now what does determine that finally the synergy between them is still changing? Well, for that, we need to look most specifically at this term right here, where we do not control the EV, but we do control the battery. Because if we control the battery, then if the charging power of the EV goes up, that means that the worth of controlling the battery also goes up. Why is that? Again, if we look at this plot, we see the charging peaks of the EV here. If we control the battery, then what it's going to do is it's going to shape the peak of, or the highest peak from the profile of the EV. Now, because we took the 2 norm of the profile, we assigned the highest penalties to the very high peaks. So if this peak is higher, because the EV charging power is higher, then the worth of the battery decreasing that peak by a little bit is, relatively speaking, worth more. So that's why this value here goes up. But because there's a minus sign in front of it, because we're subtracting it, that means that the worth of the control of the battery going up means that finally the interaction between the EV and the battery, that will go down. So that's why we see these 2 plots and why there's such a big difference between when we have a very high charging power or a low charging power for the EV. And this is just one very specific result that I wanted to dive into today with you. There's a lot more of such evaluations in the paper, so please make sure to read that. But for now, I just want to go to the conclusion. So I think that based on the results that I've shown you here today, for household winter peak flattening in this Dutch scenario, EV is the most important asset to control. And then more importantly, I think that if we look at these approaches that we described, then synergy can really describe what the worth is or the redundancy of the cooperation between devices, which is a very interesting result. And then on top of that, the Shapley value itself is also a very promising method to quantify flexibility in energy applications. And this is not just for what we discussed here with the 2 norm flattening. It can be used for all sorts of flexibility applications as well. Then finally, as a take-home message, I just want to say that I think in demand-side management policy, it's important to focus on these 3 devices because the others aren't that important, relatively speaking. I think we've shown that here today. That's where I want to stop it here. So I would like to answer any of your questions. So thanks for listening.